Okay, so today we're going to talk about electron configuration. So before I get into that, we're going to kind of label the periodic table. Um, Not kind of, we are. So things that we know already is the periods go from 1 to 7, left to right. And then you have groups going in columns. I didn't really expand too much on it, but we're going to make a little key at the bottom. So we're going to have S block. I'll do pink as the P block. And then we'll do, I guess blue for, we'll do blue as transition metals. Okay, and then we're going to highlight for metalloids. I'm going to just do green. And I'm going to change that from blue to black. And we'll get started. Okay, so first thing we're going to do is just kind of label everything. Our group 1 is going to be in red. Not group 1, the S block. Wow, I cannot draw today. That's fine. So I know this is over here, but this technically belongs, even though it's a noble gas, it is part of the S block. So our P block goes from here to here. And our transition metals go from here to here. Okay, and then now our last thing is metalloids. Metalloids, you have boron, silicon, germanium, arsenic, antimony, and tellurium. I already kind of went over what a metalloid was when I talked about the periodic table. I just didn't really label them. But they're elements that have properties of both a metal and a non-metal. Alright, so next thing I want you to do is whatever color you want to do. You could see that the groups are labeled 1 through 18. We don't really need those top numbers in the transition metals so much, but they're very helpful here. So you can either cross the 1 off or cross the whole number and rewrite it, which is what I'm going to do because you can't really read it. So and the reason for that is you don't really have to group the transition metals, but this will make counting for your electron configuration much easier. And before we get started on that, the last thing I want you to do is write the charges. I know it's kind of cramped here, but just do your best. Okay, so the charges are for if it gets ionized, that's going to be the most likely charge that element takes. So group 1, anything ionized, it's going to be +1. Group 2, +2. And so on. Excuse me. Okay, so now, what I want you to do, just copy this and I'll explain it, because we're going to be jumping back and forth a lot. Color, I'll just do black, it's fine. Okay, so your s orbitals and your p orbitals. If you remember from when I went over quantum numbers, you have slots. And those slots correspond to m sub l. So you have S, P, and I'm not even going to go over F right now. But you could see that you have 1 slot, 3 slots, and 5 slots. Each of these slots can have 2 electrons in it. So I'm just going to fill these out. We'll go over that later. But as you can see, S1, S2, S1, S2. So it's these numbers with the S and the P are literally referring to an electron. Whereas your P, if you count, you have 3 through 8. That is 1, 2, 3, 4, 5, 6. So you can have 6 electrons in your p orbital. Your d orbital, I'm not going to write them, but you can have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then, I'm not going to write it down, but your f can have 14. So that was just to kind of help you understand what we're going to do. Now, with your electron configuration, we're going to make a table real quick. Probably about like 10 spaces or something like that. I haven't really decided yet. But your table is going to help you understand how to do electron configuration. I promise you it is super, super easy. I'm going to write it up here. You guys are probably thinking, oh my god, this is so much information. It is, but this is not hard. I promise you, it's literally counting. If you can count, you'll be fine. So, there's 2 types of notation for electron configuration. You have long notation, and you have short notation. So you're not going to be able to have short notation until you pass helium, but like honestly, it's kind of pointless until you're past, I think it's beryllium. I don't have a periodic table in front of me, so. Anyways, we're going to start off with hydrogen because it's the first element. So I'm going to go back to the table and we're going to explain this. So the electron configuration of hydrogen is 1s1. There's no short notation. So we're going to do helium now. I'm going to jump back. So you're literally counting. I know that says P6 over here, but technically that would be the S2. And that's the only case like that. So 1s1, 1s2. So instead of writing 1s1, 1s2, you write 1s2, and that's explaining that you have 2 electrons in the s orbital. Alright, we're going to do lithium now. So lithium is down here. So you have 1s2, 2s1. So there's 2 ways to write this. Like I said, the long or short notation is kind of pointless, but I think it's actually more work. So when you do short notation, you take the noble gas from the previous period and you put it in brackets, right? And then you write the valence shell. So your valence shell is just going to be 2s1. And that would be how you would do the notation. So what this is saying is you have the electron configuration of helium plus a valence shell of 2s1. That's literally all it's saying. So now we're going to do beryllium. That's 1s2, 2s2. And then this would be He, 2s2. It's really not hard. You're just counting. But we've only done s orbitals, so I'm going to do 1 p orbital, and then I want to see if you guys can try and do some on your own. Wow, I keep going ahead. So let's do boron. So we have 1s2, and then period changes, so we're at 2s2, and then 2p1. So we have for boron 1s2, 2s2, 2p1. And these numbers, if you count, will be the number of electrons that that element has. And its valence shell is going to be here, which it makes sense. So you have 2, 4, 5 electrons. So the short notation would be He, 2s2, 2p1. So that's when it starts to get, a little easier to do the shorthand. After you get past period 2, if you're not doing the shorthand, you're doing way too much work. Unless I ask you to do a long notation just to make sure you know how to do it. Alright, so I'm going to do carbon, and then I'm going to write a few down and give you a few seconds to do them. I'm going to tell you to pause the video. I want you to try them on your own, and then I'm going to just write them in. And then, I'm going to write the rules down for the short notation, and we'll call this good. And, electron configuration is super easy. And then after that, we're going to go over electron configurations for ions. It's not too much different, but I'm going to do a separate video for that. Alright, so carbon is 1s2, 2s2, 2p2. Alright, so I'm going to write a few down. Seven is nitrogen, oxygen. Alright, and then I'm going to give you a few in the next period that I want you to try. We'll just pretend that that's super straight like the other lines. We'll do... Alright, so pause the video and try this. I want you to try both the long and shorthand notation. Okay, so I'm going to just go ahead and start writing these in. I'm going to do the longhand notation first. And I know I said I was going to do a separate video for the ions, but I'm going to just do it all now. Doesn't really make sense. Oh, wow. Why am I writing 2p? Jeez, I am tired. Okay, so... even if you don't really remember it, if you have this as a guide for your homework, you should be able to kind of piece together what's going on and use your periodic table to, fill the answers in. And once you get the hang of doing this, it's super easy. So I'm going to go back to the periodic table for phosphorus, and we're going to do this one. 1s2, 2s2, 2p6, 3s2, 3p3. So this is where the long notation starts to become kind of tedious and annoying, and I don't like doing it, but it's personal preference if you like doing the shorthand notation. So for here, we go to the previous noble gas, which is neon. Put that in brackets, right? So, and then you have 3s2, 3p3. And then for chlorine, long notation is very similar. And the shorthand notation is very similar. So if you have any questions about how to do that, first try and figure it out yourself and then ask me, because I found that if you're able to kind of piece together how to do this on your own, it becomes a lot easier for you than just asking me to show you, because I know how to do this. So it's really just like counting. Alright, so we're going to go over the rules for short notation, even though I already showed you how to do it. I'm going to write them down. So, 1. We locate the element on the periodic table. 2. Go to the previous noble gas. And previous means previous period. And then 3, you write the symbol of that noble gas in brackets. and then write the valence shell, or the valence electrons in the electron configuration. So write the remainder of your electron config. And I'm going to make a note that the remainder of it is actually your valence shell. So valence. Okay. We're going to go over real quickly how to do this for ions. It's not much different. It's actually easy. Just involves like a little addition, subtraction. But it's really not too bad. Alright, so remember for ions, you have positive and negative. And if you do not remember that cat meme, I'm going to be very mad. So, because that's one of my best jokes that wasn't even mine, but gets them every time. So, it's losing electrons and then gaining electrons. Alright, so we're going to go over just ions super quick and then transition metals and we'll be done. It's not going to be too hard. So what I'm gonna do instead of just doing ions, I'm gonna write the electron configuration of the pure element and then the ionic version of like 2 or 3 and then give you examples to try. Alright, so I'm also not doing the long notation because, oh wow, element. I cannot write today. Alright, so we have element and then electron config. Yeah, I want you to get comfortable with the shorthand notation because it's more important to me. But, so we're going to start off with sodium. So sodium, if you remember from the periodic table, is in period 3. So that means that we have to go through a whole bunch of crap to get there. So we're just going to go brackets neon 3s1 because it's way easier to write. Okay, now that we have our electron configuration for the pure element, go back to the periodic table. Think about it for a second. What should the charge of a sodium ion be? If you look up to where I wrote the charge, you would know that it's going to be +1. So it's going to be a cation because it's positive. So that means it lost an electron. So if it lost an electron, it's going to lose from its valence shell. Where do you think that is? And I did a horrible job of asking that question because I literally had my cursor right under the answer. But it's going to lose its S1 electron in the 3rd period. So your new electron configuration is literally this. And if you want to do the longhand notation, it would be 1s2, 2s2, 2p6. It's going to have the same configuration as neon because it's stable. Neon's a noble gas. That's the whole idea with ions, is they're trying to become stable. So, alright, we're going to have elemental magnesium would be neon 3s2. So, if you add the ionic version, it's going to lose 2 electrons to get to neon because that's what it's trying to do. So, it's going to be Mg +2. So that means it lost both of these. So it's going to be Ne, and that's it. Or this same thing. Alright, I'm going to do one where we have an anion, and then I'll write a few for you to try, and then I'm not even going to go over the answers or anything. Actually, no, I'll go over the answers. That'd be messed up. So you have chlorine. Chlorine would be, from last page, we have 3s2, 3p5. So it doesn't make a whole lot of sense for chlorine to go all the way back to neon. That does not sound stable. What does sound stable if it was trying to gain an electron to get to argon? Because if you notice that its ionic version has a -1 charge, the reason for that is all of these elements are trying to have an octet of electrons. So chlorine is going to be Cl -1. So you have Ne, 3s2, 3p6. It gets the elemental configuration of argon. So, I mean, that's pretty much how electron configuration works for ions. It's not too difficult. It gets a little wonky when we talk about transition metals, so try these on your own. You should be able to do this fairly quickly. So pause the video for a second and try this, and then I'm going to go over it. Alright, so for this one, we have, let me look at the periodic table because I don't remember. Yeah. So you have, it's kind of pointless to do this, but. Alright, and then for the ionic version, you're getting the configuration of neon. So you would have this, and you would gain 3 electrons. Potassium has the electron configuration of argon, and it has 1 electron in its 4s orbital. And for K+1, it's the same as these. It loses an electron, so it loses that electron there. I'm not going to write the longhand notation. It's kind of, you should know how to do that by now. Alright, last thing, transition metals. I think I already talked about these. If not, then nope, I did not talk about these in terms of naming them. That's okay. So for transition metals, I'm gonna just explain. Transition metals have your d orbitals, but if you remember from quantum numbers, d, the L value for that is 2. So that means that by period 3, you have d orbitals. They're just not being filled because they're not needed. So your transition metals are able to have altering charges because they fill these d orbitals out. I'm going to show you a few. We're going to probably go over this more in class, but so we're going to make a table real quick. Just a small one. I'm not going to even worry about the straight lines or anything. Okay, so I'm going to do this. We'll do iron. That's always popular. And then I'm going to do zinc. And we're going to do the 2 exceptions. I don't know why they're exceptions. They just are. There's something weird about the way that they form a stable element. But anyways, so you're just going to have to remember these 2 right here. Alright, so essentially, if you have a period 4 element, your electron configuration is AR and then 4 ... whatever. So for a transition metal, you would think that because we're filling out 3 d orbitals, they would go before the 4s, but they do not. So you're going to start out like this. Remember, it's just like counting. So I know this is in period 4, but these are actually 3D orbitals. So say we were going to do number 22. We have argon in brackets, 4s2, 3d1, 3d2. And that is how you would write it. It's really not complicated. It's just a little weird. Alright. So, for iron, you still have this, and you still have this. But now we have to go back to the periodic table and count where it is. 3d1, 2, 3, 4, 5, 6. So that means that you're going to fill out your orbital for 3d6. And then zinc, because it's 30, and it's the last element there, we know it's going to be 3d10. If you don't believe me, you can count, but I've been doing this a while, so. Alright, I'm just trying to save time on the video. Now, for our special cases, you would think that this would be 4s2, 3d4. It is not. The stable configuration for this is 4s1, 3d5. I don't know why that is. It just is. It's an exception. And then for copper, it is 4s1, 3d10. I'm going to have to look into why it's like that. I've tried before, but I haven't really found any papers about that. I'm not going to really talk about period 5 too much. It's more of the same. You would just, for period 5, it would be, you'd have krypton, 5s2, 4d, and then x, whatever that number is. There are exceptions in there, but I'm not really going to be asking you too much about that. And that's really it for, electron configuration. It's not too complicated. And it goes hand in hand with understanding quantum numbers. So if you have any questions about this, I know it was a lot of information, please ask me. And I'll see you in the next video.